All right, everybody, and welcome to a continuation of hyperbolic trigonometry. So this is where we stopped at last time. And as we know, the trig functions for hyperbolic sine and cosine, they were defined, uh, well, they're defined right here, and there's also uh, formula sheets that will give you derivatives, the familiar trig identities, and then the functions for inverse hyperbolic trig functions. I'll go over one of them much later, but I'm going to go over the sort of the basic trig functions that you might see. So there's also the reciprocal functions that you might be able to recognize. And one of them is, let's start off with secant, hyperbolic of x. This is 1 over hyperbolic cosine, right? And so the exponential definition is 2 over e to the x plus e to the negative x. Now its graph, I'll just draw a little bit of a graph here. Just looks at what the M behavior of this function would look like. So this is x and this is y. If you notice, the terms in the denominator, excuse me, it will never be 0, right? E to the x is an exponential function, right? So it will never be 0. It can't approach to 0, but it never does equal. There's no x value that makes the denominator be 0. So right away, the domain is all of the real numbers, right? All the real numbers. Okay. The second thing is, if I want to look at the hyperbolic secant of 0, well, that would be 2 divided by e to the 0 plus e to the minus 0. Well, that's 1. So 2 over 2, which is 1, right? So secant hyperbolic at 0 is 1. So we'll cross at the y-axis at that point, okay? So, excuse me. As x approaches to infinity, let's see what happens, right? As x approaches to infinity, right? This is 2 over e to the x plus e to the minus x. So e to the minus x, this will go to 0, right? And then since we can rewrite this as 2 over e to the x plus 1 over e to the x, right? Since this term goes to 0, right? Also, 2 over e to the x will be a much smaller number. So this would approach to 0, right? So all in all, the limit as x approaches infinity of hyperbolic secant would be 0. So what's going to happen is these values will get smaller and smaller. Approach to 0 like this, right? On the other hand, if x goes to negative infinity, well, this term will be smaller, and this term will become positive, and this will be 0. So nevertheless, the whole term will go to 0. So you'll have this type of graph, right? So this is hyperbolic secant. This is the graph of hyperbolic secant. How about hyperbolic cosecant? Now this one is, by definition, this equals to 2 over e to the x minus e to the minus x, right? Now, here is the issue. So we'll have one value of x that will make this undefined. Do you know where it is? Well, it's at x equals 0, right? X equals 0 will be undefined, right? So we will have a vertical asymptote at x equals 0. So let me just draw in the asymptote like this at x equals 0, and well, on the y-axis, I should say, right? So we'll have an asymptote at x equals 0, right? So it's undefined at x equals 0. All right. So if we look at what happens if we approach 0 from the right-hand side, that's when x is greater than 0. Well, you notice that e to a value that is closer to 0, it would be a much so it will approach to 1 essentially. So right, if I just look at e to the x itself, right? So if I look at 0 to the right of e to the x, well, this will approach to 1, right? So, however, if I look at e to the minus x, if x goes to infinity, this will go to 0. I'm sorry, when it goes to 0 for the right-hand side. So, right, so this, what this means is, okay. E to the x will be a much bigger number than e to the minus x. That's what I'm saying, right? So it's going to shoot off at positive infinity, and then when x gets a bigger number, right, bigger than 0, well, e to the x is bigger than e to the minus x. So essentially, this piece will go to 0, right? So it's sort of similar to 1 over x, the curve of 1 over x, but it's not. So it's hyperbolic cosecant. It has a lot more curvature. So we can derive at the similar issue when we are approaching at 0 from the left-hand side. When we're approaching 0 from the left, this will become a bigger number, right? And so it will shoot off towards negative infinity. So down here, oops. So it will shoot off down here. And when x approaches to negative infinity, this term right here, oops. This e to the x term here will go to 0, right? And then e to the minus x will be a lot bigger number. So it will shoot off towards negative infinity that way, right? So that's the graph of hyperbolic cosecant of x, right? Cotangent, hyperbolic cotangent, well, by definition is hyperbolic cosine divided by hyperbolic sine of x. So this equals to e to the x plus e to the minus x divided by e to the x minus e to the minus x. Okay, so again, we will have we'll have a vertical asymptote at x equals 0, and we're going to have two horizontal asymptotes. Okay, so one of them is at y equals 1, and the other one is at y equals negative 1. Okay, I want you to figure that out on your own, why that is. Okay, horizontal asymptotes refer to the end behavior of a function. So we want to examine, excuse me, what happens if x approaches to infinity or negative infinity, right? So So we'll have asymptotes here at y equals 1 and that y equals -1. This is x and the y-axis here. And our graph will look like this. Okay. Oops, let me draw that again. All right. So the graph in green here is hyperbolic cotangent of x. Okay. Hyperbolic cotangent. Excuse me. So yeah, so that would be the graph for hyperbolic cotangent. So hopefully that made sense. So what I want to get into next is on inverse trig functions, inverse hyperbolic trig functions. So hyperbolic trig functions. So I will show you one example of algebraically the functions for a hyperbolic trig function. I'll do inverse sine, but essentially the operations for the hyperbolic inverse tangent and hyperbolic inverse cosine will work the same way. Okay, so in order for an inverse function to exist, we want to check whether the function is one-to-one, right? So as you can see, to check for a one-to-one function graphically, you want to use the horizontal line test. What this is, you draw a horizontal line across your graph, and it has to cross the graph exactly once. If it crosses exactly once, it will be a one-to-one function, right? Thereby, you can conclude the function has an inverse. If there are regions in your graph that cross that a horizontal line crosses more than once, it's not a one-to-one function. So in this case, hyperbolics sine and tangent are one-to-one functions everywhere. And then hyperbolic cosine is not one-to-one everywhere. So we need to restrict our domain for hyperbolic cosine to become one-to-one. So in this case, if I restrict my domain for the inverse function for cosine, to all values that are greater than 0, then yes, we will have a one-to-one function, right? So, and so we can define an inverse function for hyperbolic cosine for every x value that's bigger than 0 and equal to 0, right? Hyperbolic sine and then hyperbolic tangent are one-to-one everywhere. I shouldn't say everywhere, on all real numbers. So on the all real number line, right? So an inverse function exists everywhere, okay? Now, here's how we go about to finding an inverse function. I'll start off with inverse sine, okay? Because an inverse function is a mapping. So a function, so let's do a review here real quick. So if I call my domain D and this other set R, we'll call it range, A function is a mapping that maps one point in your domain to another point in the range, right? So I call this one x1 and this one is y1, right? What this means is that y1 is equal to the function at x1, right? So a function is a mapping from one point or an element in your input set, we'll call the domain, right? And it maps to another point, exactly one point, in the output set, which is the range, right? Y1 equals F, and this mapping is associated by this notation, right? Okay, so an inverse function is the opposite of an ordinary function. What we want to do is we want to figure out points that are in our range that get mapped to points inside of our domain. So an inverse function is saying, well, x1 is equal to f inverse of y1, right? This notation is the inverse of f, right? Okay. So that's just a review on inverse functions. So for inverse trig functions, so if I call inverse sine of x is y, I'll say, right? This corresponds to, this is equivalent to saying, well, x is equal to inverse hyperbolic, I'm sorry, x is equal to hyperbolic sine of y. Okay. By definition, x is equal to e to the y minus e to the minus y over 2. Okay. And from this point, we want to solve for y. Okay. So that means if I cross multiply, I'll get 2x equals to e to the y minus e to the minus y. Okay. From this point, I want to multiply both sides by e to the y, e to the y. So what we'll get is 2x times e to the y equals to e to the 2y minus 1. Okay. You might see where this is going. Okay. But here, what we have is we'll have a quadratic expression in terms of e to the 2y, right? E to the 2y. Right, we have e to the 2y, we have e to the y here, and then e to the y raised to the 0 power here, right? So that's a constant. So what I can do is apply a u sub. So if I let u equal e to the y, that means if I square both sides, I'll get e to the 2y, right? So that means 0 is equal to e, u squared minus 2x times u minus 1. Okay. All right. Good. So now we want to use the quadratic formula to solve for the roots for u. So u is equal to 2x plus or minus the square root of minus 2x squared minus 4 times 1 times negative 1 divided by 2 times 1. Okay? So u is equal to, so I will have x plus or minus, so I'll have, or I should write out 2x, plus or minus 4x squared plus 4 over 2. So this would mean that u is equal to 2x plus or minus 2 times x squared plus 1 over 2, which means if I divide all those by 2, we'll get u is equal to x plus or minus the square root of x squared plus 1. Okay? Since u is e to the y, we'll have e to the y is equal to x plus the square root of x squared plus 1. Or e to the y is equal to x minus the square root of x squared plus 1. Okay? Hopefully that makes sense. Now, what we want is this y value to be positive, right? Okay, so e raised to a number will always be a positive number. Okay, it's an exponent. So right away, we can say that y is equal to the natural log of x plus the square root of x squared plus 1. If I take the natural log of both sides of this expression, if I take the natural log here, I should get this, right? But here, for this expression, the square root of x squared plus 1 is greater than x squared, right? So this will result in something that is negative. Okay, so we disregard. So we disregard this root, okay? Since y was equal to inverse sine of x, we can notate what inverse sine, hyperbolic sine would look like. So it's equal to the natural log of x plus the square root of x squared plus 1. Okay? And our domain for the inverse function is everything, so that means the domain is all of the real numbers. Right? Okay. Now, I want you to try on your own how to formulate inverse cosine. So this is the natural log of x plus the square root of x squared minus 1. Right? And remember, this has to be greater than or equal to 1, right? Since the ordinary cosine function was restricted to the domain that x is non-negative, right? So I want you to try this on your own and make sure if you derive this correctly. If not, just let me know, okay? And then what I want to go over is how to take the derivatives of inverse trig functions. So let's look at derivatives of inverse hyperbolic trigonometry functions. Okay, so let's look at how to differentiate inverse sine of x, right? Okay, I mean, one way is just using the chain rule, right? On how to so yeah, using the chain rule twice, right? Or 3 times, I should say. Yeah, twice, right? So you can use chain rule twice to get the same result, right? The other way is we can use the definition of an inverse function, right? So if I let y equals to inverse hyperbolic sine of x, this is equivalent to saying that x is equal to hyperbolic sine of y, right? So this strategy is useful for all the other inverse functions to do, right? And this is an application to implicit differentiation. So if I suppose that y is a function of x, okay, what we have to do is we have to use a chain rule for y. So here's how we do it. So with respect to x, the derivative of x is 1, right? So if I differentiate both sides, okay, I'll get 1 is equal to, well, we have to use the chain rule. This derivative of hyperbolic sine would be hyperbolic cosine. And we need to differentiate y, which is dy dx, okay? Dy dx. Next, we want to solve for dy dx. So that means dy dx is equal to 1 divided by hyperbolic cosine of x, right? But we want to write this in terms of hyperbolic sine since we're referring to the inverse hyperbolic sine. So what we're going to have to do is write out this quantity here in terms of hyperbolic sine. Well, recall one of your trig identities, hyperbolic cosine squared minus hyperbolic sine squared of x equals 1, right? So hyperbolic cosine squared of x is equal to 1 plus hyperbolic sine squared of x. Hyperbolic cosine of x is equal to the square root, or plus or minus, the square root of 1 plus hyperbolic sine squared of x. Okay. So as you know, the hyperbolic cosine function, this is a positive function, right? So we disregard the negative sign. So we can rewrite hyperbolic cosine, I should say this quantity now, as dy dx is equal to 1 divided by the square root of 1 plus hyperbolic sine squared of x, right? But sine squared of x, sine squared of y, I meant y here. I meant y, so this is y here. So this would equal to, since sine, hyperbolic sine is of y is x, we can write this product, this quantity as 1 divided by the square root of 1 plus x squared. Okay. And that is the derivative of inverse hyperbolic sine of x. You can write it 1 divided by 1 plus x squared or 1 divided by x squared plus 1, right? Since you're adding terms, it's commutative, right? So you can write the denominator in either order, right? So, yeah, and also since the inverse function is defined everywhere, the domain wouldn't have any problems. So the domain for x is all the real numbers, okay? But essentially, this is how you differentiate inverse sine of x, right? You can do this same method to derive all the other inverse functions. So I don't have that here, but it's in your textbook. So yeah, so the derivative for hyperbolic cosine in this case would be 1 divided by the square root of x squared minus 1, right? X has to be greater than 1 here, okay? And then you can derive all the other inverse functions in theorem 7.8 in your textbook. Okay. And I will include those a little bit later. But yeah. So mostly your homework assignments will be dealing with the derivatives and integrals of ordinary trig functions and their inverses. Okay. So I will include all those formulas much later, but this last tidbit, I want you to work on these examples on your own. Okay. I will come back to work with these later. So this one. So number one, I want you to figure out the derivatives and or integrals of these functions. So I want you to figure out the derivative of x times hyperbolic tangent. Inverse sine of tangent. Figure out the integral from 0 to 4 of hyperbolic secant of the square root of x divided by the square root of x dx. Dx divided by x times the square root of 16 plus x squared. And this will be dealing with a word problem. So these hyperbolic trig functions come from building bridges. Catenary is actually Latin for chain. Okay. And most modern day bridges are built in a catenary fashion, right? So they have an ordinary cosine curve, hyperbolic cosine curve, excuse me. Catenary. And I want you to find the average height of the arch above the x-axis. And the hint here is the average value, they call this f bar, is equal to 1 over b minus a divided times the integral from a to b of f of x dx. This is what's called the average value. Okay, it's the average value. So let me scroll back out. So I want you to work out these problems. You can pause the video if you want to, but I'll just end it here. But and I will talk about these problems much later. So once again, if you have questions, just let me know. Otherwise, I will see you later in the next video. So thank you for watching, and I will see you soon.